All right, so with module 2 here, we are going to be looking at a little bit more of a chemistry focus than what we did in the previous module. So, we talked about matter in module 1. We're talking about very generic kind of physical science definitions of matter and energy. Here with module 2, we're going to start getting into looking at some more chemical kinds of things and getting turned more onto a chemistry focus. But one thing I do want you to understand, I do want you to know. So the first 4 sections of this module are kind of the history and background of atomic theory. And we're going to kind of buzz through those very quickly here today. We're not going to spend a whole lot of time on them because other than a few key aspects, none of them are super important enough to make a big show of time on. If this is something that interests you, I have another video in my YouTube series where I go through a much more long-form view of the history of atomic theory. There's some really interesting stuff in it. But for our purposes, I would just ask you read through those sections and just kind of glean some of the stuff from it that might be useful to us. But for the most part, we're not going to spend a ton of time on. What we will spend some time on is some of the highlights from that section. And so one of the highlights of this section is the first atomic theory proposed by John Dalton. And in this atomic theory, you're going to find some things that you recognize and that you know. So first of all, in Dalton's atomic theory, we hear that matter consists of atoms. This is something that, again, we already kind of knew, and that as the smallest identifiable unit of matter, it cannot be created or destroyed in any kind of process. Another key piece of this atomic theory is that all atoms of the same element are identical to each other. But atoms of different elements have some sort of different differentiating factor between them. And then finally, the last piece of this atomic theory that's really relevant to us is the idea that when compounds are made out of these atoms, they always make in this whole number ratio that is very predictable. So when I make a compound of carbon dioxide, it is always 1 carbon and 2 oxygens. No more, no fewer, always the same ratio of 1 to the next. So this is the atomic theory. And again, this is 1808. We're talking about some very rudimentary kinds of thought on this without really the benefit of technology to take it much further than this. But out of this atomic theory, we are able to build what are called the 3 fundamental laws of chemistry. And those 3 fundamental laws of chemistry are the law of conservation of matter, which we have previously discussed, the idea that matter cannot be created or destroyed. Now, this law of conservation is also equally applied to mass and to energy. And so sometimes we refer to this conservation law as the law of conservation of mass, and sometimes we refer to it as the law of conservation of energy. And the key idea in these conservation laws is that although we can conserve the mass and energy of a system, that mass and energy can interconvert in between each other. So if I look at a chemical process, The total mass of all of the stuff that was there at the beginning equals the total mass of all the stuff there at the end. But that doesn't necessarily mean that the compounds that were there at the beginning are the same as the ones that are there at the end. Those atoms have the ability to move around and make new compounds, different arrangements of atoms as we go from reactant to product. The energy component, one of the pieces of module 1 that we didn't really touch on, but was kind of there in the background, was the idea of energy. Energy can basically split into 2 different areas. There is the energy of motion, kinetic energy, and there is the stored energy, potential energy. And in a chemical process, that energy can go from kinetic to stored. It can go from stored to kinetic. It can go in 100 other different directions: sound, light, heat, bonds, nuclear energy. It can go in a lot of different directions. But if I look at the whole thing as a total, the total amount of energy does not change. It just gets redistributed or reconfigured from one idea, one phase to another. So that's our conservation law. That's one of the laws that was derived out of that atomic theory. Now, another derivation is something called the law of multiple proportions. The law of multiple proportions tells us that when we have an element combining with other elements to make multiple compounds, the ratio of one element to another is always going to boil down to some whole number ratio of the 2 elements to each other. So in the case of these 2 compounds, I've got hydrogen and oxygen mixing and combining in both cases. In the first case, we've got water. Water is combining in a ratio that is 2 hydrogens to 1 oxygen. Hydrogen peroxide, on the other hand, is combining in a ratio that is 2 hydrogens to 2 oxygens. They are 2 different compounds. They have 2 different relationships of mass and 2 different atomic relationships in terms of their ratio. But even though their relationships are different, when we distill down the compound to the atomic level, what we find is that the ratios still come out to be whole numbers. 2 to 1 for water, 1 to 1 for the hydrogen peroxide. That's the law of multiple proportions. Multiple compounds can be made from multiple elements, but the ratio always comes down to a whole number relationship between one element and the other. This is similar, yet slightly different from what is called the law of definite proportion. The law of definite proportions, also known as the law of constant composition, focuses on an individual compound will always have the same mass ratio of one element to another. And this mass ratio being held consistent has everything to do with the fact that its atomic ratio is consistent. So if I look at water, the mass composition of water is 11% hydrogen and 89% oxygen. That composition of water is consistent regardless of what the water is. Doesn't matter if it's in the ice phase, the steam phase, or the liquid phase. It doesn't matter if I have a tablespoon of that water or an ocean full of that water. Regardless of the form, regardless of the amount, that mass ratio is always the same. That is the consistent part of this constant composition. So these three fundamental laws are born out of Dalton's atomic theory. And that's why we focus on Dalton's atomic theory. Even though some of what Dalton said isn't 100% true, even though the atomic theory itself is incredibly generic and not very specific to what an atom looks like, because it really just describes what an atom is and what it is not. We get three really important fundamental laws out of it that kind of frame how we look at matter. Now, when it comes to what is the atom actually made out of, we looked at a couple of experiments that give us some clues and some details. So these two experiments, the experiment of J.J. Thomson in the late 19th century, the Millikan oil drop experiment in the early 20th century, what these two establish is the fact that there is a negatively charged particle inside of an atom. We call it the electron. And that particular electron has a specific charge and a specific mass. And that's what these two experiments ultimately uncover. Electrons exist. This is their charge. This is their mass. And if you want more details about how each of these experiments were done, again, go to the textbook, go to the other information I have out there. I can give you a lot more detail about how they came about. The other major discovery that leads us in the direction that most of us understand about the atom is the Rutherford gold foil experiment. In the Rutherford gold foil experiment, heavy particles are shot at this piece of gold foil. And what is determined is that most of those particles go straight through the foil. Some of the particles are deflected quite heavily, but most go straight through. This leads us to the modern or a modern model of the atom. Now, we'll expand upon this model of the atom. We will correct some of this model of the atom in module number 3. But the Rutherfordian model of the atom, the nuclear model of the atom, is important because it is still largely what we base our understanding of atoms off of. In the middle of an atom, there's this dense, positively charged center that we call the nucleus. Later experiments would determine that inside of that nucleus, not only do we have positively charged particles that we call protons, but we also have particles that have no charge whatsoever that we call neutrons. But in that heavy, dense center nucleus, that is the core of our atom. Those electrons aren't in this part of the atom, they're surrounding the atom. Which is why, if we think about why did the gold foil experiment go the way that it did, why did most of those particles shoot straight through? Well, because if they didn't hit a nucleus, they would have hit an electron. And if I look at the mass of an electron relative to the mass of the other particles, it's next to nothing. Now, the particles that they were shooting had an atomic mass of roughly 4. They were alpha particles. Alpha particles had 2 protons and 2 neutrons. So the mass of those particles was roughly 4. If they hit the nucleus of gold weighs a good bit. Weighs about 197. So if they actually hit the nucleus, it made an impact. It deflected pretty strongly. But if it didn't hit the nucleus, it went straight through. Because a mass of 4 compared to a mass of 0, mass of 0 is not even going to make an impression on its path. So from this nuclear model of the atom, we establish our 3 subatomic particles. The proton, which has a mass of 1 and a charge of positive 1. The neutron, which has a mass of 1 but no charge. And the electron, which even though it does technically have a mass, relative to these other 2, is practically massless. But its key important factor is that it has a -1 charge on it. This is the nuclear model of the atom. This is the model of the atom that we're going to focus on here in this module. And so we're going to focus on a couple of aspects of this as we kind of proceed through the rest of our discussion today. First thing we're going to focus on, the idea of atomic number. The atomic number is the number of protons inside of the nucleus. Now, this is where one of the Dalton ideas kind of ran into some friction. We're going to talk about isotopes in a couple of minutes here. The idea of an isotope is I've got a nucleus that has an equal number of protons, but a different number of neutrons. The Dalton theory didn't account for isotopes. Remember, it said that all atoms of a given element were identical. Well, we know that it's not exactly true. The part that is identical is the atomic number, the number of protons. So we can find the atomic number in our elemental symbols, and we'll always find it near the top of a symbol. So it doesn't matter if you're looking at a periodic table like this, or a periodic table like the one that's on the wall, or a periodic table like the one I'm going to give you on Friday. The atomic number is almost always in the top, and it tells you the number of protons in that element's nucleus. Now, we'll talk about what the bottom number is in a minute. It's not quite what you think it is, probably. Things that we should know, though. Atoms are, by their very nature, neutral. So, if I know the atomic number, and the atomic number is the number of protons, assuming that the atom is neutral, that number is also the number of electrons. Other key features, thing that we need to focus on, the periodic table arranges our elements by order of atomic number. Now, that's not always how it was. In fact, most of the earliest models of the periodic table arranged by atomic mass. But one of the main reasons that they did that was there wasn't enough known yet about the structure of the atom to know that protons were even a thing. So if you read about Dmitri Mendeleev and his early periodic tables, they were arranged by mass because that was the information he had available to him. The nuclear model of the atom really wasn't in existence yet. And if you look closely, the reason Mendeleev's periodic table worked is because for the most part, atomic masses follow the trend of atomic numbers. There are some weird places where it doesn't, and that's where the early periodic table kind of had some difficulty. But what if we don't have an atom? What if we don't have a balance of protons and electrons? When that is the case, we have what is called an ion. The status of an ion depends on the electrons in that atom. Ions come about when the number of protons is different from the number of electrons. So ions really don't have anything to do with the atomic number or the number of protons. I can't get a positive ion by changing the number of protons. Because if I change the number of protons, I change the identity of the element itself. So to get an ion, I have to either gain electrons or lose electrons. Now, when I lose electrons, two things happen. First of all, I end up getting a positively charged ion. We call positively charged ions cations. And the way that works from a balance standpoint is, let's look at these two. So if this was an atom of sodium, now the model here is not quite that. This is actually, if we're counting and being technical, this is an atom of lithium. Well, let's just pretend that this models this equation here. If everything is equal, I've got 11 protons because it's sodium and 11 electrons because it's a neutral atom. When I lose this electron, I still have 11 protons, but now I only have the 10 electrons because I've lost the 1 electron along the way. In the net overall viewing, I can see that I have an extra proton. And so I'm going to say that this ion carries a positive 1 charge. Now, the more electrons I lose, the more positive this charge would get. And in fact, I could keep losing electrons until I had none left. So for sodium, the highest possible charge it could take is positive 11, where it lost all 11 of its electrons and just had those 11 protons. Now, to do that would require some extraordinary effort from an energy standpoint, but we'll get into that later. So those are cations. Anions, on the other hand, are the opposite. So in an anion, we are talking about, again, a mismatch between protons and electrons. But in this case, we now have more electrons than protons. So when an atom gains an electron, the net result is that it becomes negatively charged. We call that negatively charged ion an anion. So here, let's look at, again, we'll pretend that this is actually representing an atom of chlorine here. So if this is chlorine, I've got 17 protons and 17 electrons at the beginning. I'm adding an electron to this, so I still have 17 protons, but now I have 18 electrons with it instead. I can see that I have 1 extra electron, and so that would be a net -1 charge. The more electrons I add, the more negative this charge would become. But there would be a limit to that as well, and that has to do more with how electrons are arranged in that atom, and that's a topic for another day. But the key factor, the thing that I want you to kind of walk away here from today, is if there is going to be charge, it is going to be from the electrons changing, not the protons changing. And the value and the sign of that charge has to do with what is the imbalance and how big is the imbalance. So with that in mind, I want you to try to answer this question. Simple question. How many electrons are in an aluminum 3+ cation? So find aluminum on the periodic table, element number 13, and then figure out what does that charge mean in terms of the number of electrons. When you have an answer, type it in and hit submit, and we will see how we did. Well, there can't be a negative number of electrons. So I want the number of electrons here. Not necessarily. What we'll find is that stability comes from the nucleus, not from the electrons. Chemical reactivity does come from the electrons, and that's a discussion for module 3 and then later on in the semester. All right, so let's work this out real quick. Aluminum is element number 13, so it's got 13 protons. In its atomic state, it would have 13 electrons. So if we're going to a 3 positive state, I'm still going to have 13 protons. 3 positive means 3 more protons than electrons. So there must only be 10 electrons in this ion. So that means that along the way, that aluminum must have lost 3 electrons. All right, any questions so far? You're asking questions in the moment. I like that. Keep that up. So if something comes up while I'm explaining, feel free to interrupt me and ask. All right. A couple more concepts that we want to talk about today, and are going to relate to some of that stuff we were just talking about with stability and the nucleus. So isotopes. Again, this is one of the places where Dalton's atomic theory doesn't fall apart, but it's something that Dalton didn't account for. The idea that an atom can be the same chemically, but not be exactly the same from a nuclear composition standpoint. The thing that makes an element is the number of protons. Elements can have different numbers of neutrons in them. And when they do, we call those isotopes. We identify an isotope based upon something called the mass number. The mass number is just a count of the number of particles in that nucleus. So the number of protons plus the number of neutrons. And we identify isotopes based upon that mass number. So when it comes to carbon, there are 3 naturally occurring forms of carbon. There's carbon 12, there's carbon 13, and there's carbon 14. The 12, 13, and 14 refer to the mass number of those isotopes. So if we were to break these down into what they are, in carbon 12, we'd expect 6 protons and 6 neutrons. In carbon 13, 6 protons and 7 neutrons. In carbon 14, 6 protons and 8 neutrons. All of them have 6 protons because they're all carbon. The different numbers of neutrons give us the different forms of the isotopes. Now, in addition to the hyphenated form, you can also see it used in this superscript form as well. Again, the superscript there refers to the mass number. But one really important thing that we don't want to confuse is that just because multiple isotopes exist doesn't necessarily mean that those isotopes are identical in their abundance, that they're all equally present here on planet Earth or in the universe for that matter. We can reflect this idea of how much an isotope is present based upon the concept of percent abundance. So these percentages tell us how much of that isotope is present compared to the other isotopes. And where we'll start on Friday is we will relate this concept of percent abundance more concretely to that other number on the periodic table in that element box, the atomic mass. So if you've ever wondered why the atomic masses aren't whole numbers, why they're always decimals, this is the reason why. So if you want to read up a little bit, there is one question in particular in that post lecture that looks at the difference between atomic mass and mass number. You might want to read in the textbook just a little bit to really get a good handle on what that difference is. But I will tell you it has to do with this idea of percent abundance. So on Friday, we'll do an example of how to calculate that. But for today, we're going to stop right here. And so on your way out, hit the stoplight question and don't forget about the assignment that is due tomorrow night. And just get ready for that quiz whenever it's coming. Have a great afternoon. Are you an education student? Okay, yes.